All right. Hello, everyone. Thanks for joining us. My name is Josh Henry. I'm a master's student at North Carolina State University. And today I'm going to try and help you optimize your fertilization strategy by getting phosphorus right. So first off, I want to start by talking a little bit about phosphorus fertilization in general. Phosphorus, which is denoted by the capital letter P, is one of the three primary macro elements essential for plant growth. Common fertilizer formulations typically report phosphorus in the form of phosphate, P2O5, but my research looks at elemental phosphorus, so the numbers are a little bit different. And I just wanted to explain that from the start. And I also wanted to give you the conversion factors so that you can convert between both of the different numbers. So you can multiply elemental phosphorus values by 2.33 to get phosphate value, or you can multiply phosphate by 0.43 to get elemental phosphorus. And in a commercial fertilizer formulation, phosphorus or phosphate is represented by the second number in the formula. For example, in 20-10-20, the 10 represents phosphate. And if you were to mix that at 200 parts per million nitrogen, it would provide 100 parts per million phosphate or 43 parts per million phosphorus. So let's talk about some of the current strategies regarding phosphorus fertilization. Recommendations have been changing recently, and high phosphorus fertilizers such as 20-20 and 20-10-20 have been found to apply far more phosphorus than is actually necessary. For most crops, only 5 to 10 parts per million is sufficient for compact and healthy plants. So my research has been looking to determine optimal rates of phosphorus for various greenhouse crops, and we'll go over some of those. Here, I just wanted to show you this chart of a couple of different common fertilizer formulations and the amount of phosphorus that they provide when mixed at 1 to 200 parts per million nitrogen. So if you look at that top row, 20-20 at the top there, and when mixed at 100 parts per million nitrogen, provides 43 parts per million phosphorus, or 86 parts per million when mixed at 200 parts per million nitrogen. So I just said a minute ago that I recommend typically 5 to 10 parts per million for most greenhouse crops. So obviously that 43 to 86 parts per million is far greater than you're going to want for most crops. So if you want to apply phosphorus rates within this general range, you can use 15-5-15 Cal Mag mixed at 100 parts per million nitrogen, or 13-2-13 Cal Mag mixed at 1 to 200 parts per million nitrogen. Additionally, you could alternate between two fertilizers and use 20-10-20 mixed at a low rate and alternate that with 15-0-15, or you could use 15-5-15 Cal Mag mixed at 200 parts per million nitrogen in conjunction with 15-0-15. So there's a number of different ways that you can achieve this general range of phosphorus fertilization. So now let's talk a little bit about plant growth response to phosphorus. So Dr. Paul Nelson here at NC State did some research in the past couple of decades looking at phosphate and phosphorus response in plug growth. And you can see here there's a couple of different plugs that were grown at different rates of phosphorus, ranging from a high rate on the left to a lower rate on the right. And you can see that with higher rates of phosphorus, you have a lot of internode stretch. And when you reduce your phosphorus rate, you get much shorter, more compact plants, which is, of course, a very beneficial trait for plug production. And so a lot of my research is based off of the findings of Dr. Nelson. So here, again, I'm researching here at NC State, looking at plant growth response to various rates of phosphorus. I've done some phosphorus rate studies on Alternanthera, Angelonia, impatiens, and sunflowers, and my overall goal has been to determine optimal rates of phosphorus for plant growth by determining growth plateaus. And I'll show you what some of those growth plateaus look like in a minute here. So first off, here's Alternanthera Brazilian Red. You can see I used 8 different rates of phosphorus ranging from 0 to 80 parts per million. And you can see that plants that were grown with either without phosphorus or with very low amounts of phosphorus were stunted. But with very small additions of phosphorus, you can see that plant growth definitely gets a lot greater, up to about 5 parts per million. You can see that that plant that was grown with 5 parts per million phosphorus is about as big as any of the plants get. And that can be represented on this growth plateau here. This is the data representing those plants that you just saw. And you can see that the growth plateaus at about 4.37 parts per million, denoted by those dotted lines. And you can see that number is in the red circle on the screen. And just to reiterate, 4.37 parts per million elemental phosphorus, that's equal to about 10 parts per million phosphate. So if that's what you're used to, I just want to make sure that you know that. And so looking at these same plants again, from the top view, you can see that phosphorus also has a significant impact on the diameter of the plants. And again, plants that are grown with 5 parts per million phosphorus reach about their maximum size and diameter. And again, here's another growth curve showing that. The growth plateaus at about 5.64 parts per million. So both height and diameter pretty much are reach their maximum right around 5 parts per million phosphorus. And now here's another cultivar of Alternanthera. You can see it has a slightly different growth habit, but again, it responds in a very similar fashion where 5 parts per million pretty much is the maximum height and also the maximum diameter. So you can use slightly lower rates than 5 parts per million to control growth and to somewhat limit growth, but you need to be very careful not to go too low or you will run into issues with severe stunting, such as the plants that were grown with 0 and 1 1/4 parts per million. They might be a little bit too small. So then moving on to Angelonia, here's Sungelonia blue. You can see that the different rates of phosphorus had a really significant impact on plant height and maybe even a little bit more, especially in diameter. But here looking at plant height, again, pretty much maxed out at 4.34 parts per million. So again, right around that 5 part per million range. And diameter maxed out at about 8.85 parts per million. So again, you can use rates of about 5 parts per million to control height in Angelonia, and that will also cause you to have some control in diameter because Angelonia has a slightly higher phosphorus requirement to reach maximum diameter. Now moving on to sunflowers, you can see the same kind of general trend here where plants that were grown with very low rates of phosphorus are significantly smaller. But one really interesting thing I wanted to show you here is that plants that were grown with either excessively high or excessively low rates of phosphorus did have a delay in flowering. So that is another effect that you may see. And you may not think of 80 parts per million as being excessively high, but again, that's what my research is trying to show, is that really you don't need that much phosphorus to achieve the best growth. So these general trends, you can see restricting phosphorus even by small amounts may help to achieve growth control. And at the same time, excessively high or low rates of phosphorus may lead to an undesirable delay in flowering as well as severe stunting. And so we've seen that most of the plants achieve maximum height and diameter around 4 to 5 parts per million, but some crops do have a slightly higher phosphorus requirement. So these heavy feeders, as you might call them, we'll take a look at those. Petunias and New Guinea impatiens both tend to follow this trend. So those will be the next crops we look at. Here we did 2 different cultivars of Petunia. This is Surprise Sky Blue. It represented a more trailing variety of Petunia. And you can see we used the same 8 rates of phosphorus. And this time around, the plants that were grown with 5 parts per million phosphorus were significantly smaller than the plants that were grown with 10 parts per million phosphorus. And again, it might be a little bit easier to see when looking at this top view that the plants that are grown with 10 parts per million are larger than the plants grown with 5 parts per million. But you really don't see any differences after that point. The second cultivar we looked at was Petunia neon, and obviously this plant has a much different growth habit. It's much more compact, but you can see that the plants reacted in a very similar way, where the plants that were grown with 10 parts per million phosphorus were a little bit larger than the plants grown with 5 parts per million. And so here is a chart showing the growth plateaus of Petunia Diameter. The top growth plateau represents Surprise Sky Blue, and the bottom one is Petunia Neon. You can see that the maximum diameter for Surprise Sky Blue was reached at about 30 centimeters, and the maximum diameter for Petunia Neon was about 17. So extremely different growth habits here, where one actually reached a diameter that was almost twice as large as the other. But you can see by the 2 different dotted lines, they represent where the plateau actually levels off. And so this shows that at 8.31 and 8.81 parts per million phosphorus, you achieve maximum diameter for Petunia. So even though they have very drastically different growth habits, they both require about the same amount of phosphorus, which is still extremely low. And I just wanted to show you this really quickly. How I and a lot of other researchers tend to plot out this data is with a typical quadratic regression curve. So you can see that there's 2 different curves. The top curve, again, representing Surprise Sky Blue, the bottom curve representing Petunia Neon. And by the look of this chart, you could say that maximum diameter was reached around 50 parts per million, which is, of course, much higher than what the growth curve I just showed you looks like. So I just wanted to plot them on top of each other just to show you that there's two drastically different models that both, so one says about 8 parts per million and the other says about 50 parts per million can be used for maximum diameter. And so these growth plateaus are typically used more by agronomists, and I think they show a much better and more accurate representation of what's actually happening here. Because what we've seen visually is that past 10 parts per million, you don't really see that increase in growth. And that's not what those quadratic curves show you. So the plateau model definitely has a better representation and gives you a better idea of how much phosphorus each crop needs. So moving on to New Guinea impatiens, we did 2 different cultivars of this as well. Pure Beauty, red on pink here, representing a more dark leaf variety of New Guinea impatient. You can see that the plant that was grown with 5 parts per million phosphorus does look significantly smaller than the plant grown with 10 parts per million phosphorus. And you see a very similar trend with Tamarinda Dark Red. So here, this is representing a more green leaf variety. Another thing I wanted to point out, again, is that the plants that were grown without phosphorus did not flower, and also they had a really interesting change in leaf architecture. You can see that the plant that was grown with 0 parts per million phosphorus, the leaves are much more upright, so very, very low rates of phosphorus can have a significant effect on how the plant actually looks. So when comparing the growth curves of height, they are both very, very similar between the 2 different cultivars. Both cultivars reached a maximum height at around 20 centimeters, and they did so using concentrations of about 10 parts per million phosphorus. Diameter, on the other hand, Pure Beauty reached a maximum diameter at almost 15 parts per million, and Tamarinda Dark Red reached its maximum diameter at about 10 parts per million. So there's a little bit of difference between cultivars sometimes, and that's a good thing to show. So it's really important to know what cultivar you're growing, because that may indicate that you want to use a different concentration of phosphorus. So here I just wanted to make a little table to show you the maximum rates of phosphorus that you want to use for some of the crops that we just looked at. Alternanthera reaches maximum height at 5 parts per million, and the same for max diameter. Angelonia reached a maximum height at 5 parts per million as well, but a maximum diameter at around 10 parts per million. And New Guinea impatiens reach a maximum height at 10 parts per million and a maximum diameter at 10 to 15 parts per million. And Petunia, we didn't measure height because it's a more trailing plant, so diameter, maximum diameter was reached around 10 parts per million. And again, I just wanted to reiterate, 5 to 10 parts per million elemental phosphorus is equal to about 12 to 23 parts per million phosphate. So if phosphate is what you're used to, that's kind of the general range that you're going to want to stay in. So now we're going to talk a little bit about phosphorus deficiency, because if you go too low with your phosphorus rates, you may run into issues with this. And typically, phosphorus deficiency symptoms occur on the lower leaves, and most people recognize phosphorus deficiency as being a red coloration of the lower leaves. And even though you may have red coloration, it's important to know that there's a number of other things that may lead to these types of symptoms, and we refer to those as mimics, and we'll go over a couple of those as well. Now, in addition, you may see symptoms of olive green leaf spots and necrosis on the lower leaves. It's not something that people typically recognize as phosphorus deficiency quite as often, but it is actually very common, just not really recognized. And then we'll go over upper leaf symptoms of phosphorus deficiency, which are quite unusual and have been a topic of my research over the last year and a half. And so these upper leaf symptoms can pretty much take on the appearance of any of the lower leaf symptoms that you would see. So reddening, spotting, chlorosis, and necrosis are all symptoms that you may see in this really unusual type of deficiency that I'll talk about. So first, I just want to illustrate the movement of phosphorus within a plant using this little mum. And notice that it's not flowering, because that'll come into play later. So here you have fertilizer that's being supplied, and the fertilizer contains phosphorus. And when you fertilize it, the roots take it up, and it moves up the plant and works its way into the upper leaves, as the lower leaves have already matured and the upper leaves are still expanding and maturing. So this is the normal movement of phosphorus within the plant. But when you cut off phosphorus, what happens? What you see is that when the substrate runs out of phosphorus and the roots can't take it up anymore, that the phosphorus that's incorporated into the lower leaves actually moves up the stem and then goes to the upper leaves. And this is because phosphorus is a mobile element. So that's why you see the symptoms of purpling or reddening, necrosis, and olive green leaf spots developing on the lower leaves, because the phosphorus is becoming deficient in those tissues. So first, let's talk a little bit about the red coloration. And here is a poinsettia leaf displaying really classical symptoms of phosphorus deficiency. You can see the overall reddening, and this is definitely a very common symptom that you'd be likely to see. So here are two New Guinean patients. The plant on the left was grown without any phosphorus at all, whereas the plant on the right was grown with a constant concentration of phosphorus. And the plant on the left, you can see, is extremely stunted. It has very red coloration, and the leaves are also stunted. So these are just some of the general symptoms you'd see with a severe phosphorus deficiency. And in addition, like I said, a reddening or a purpling, they both can kind of occur. It depends on the species of plant that you're looking at. It depends on the cultivar, and it depends on the severity of the symptoms. So here on this mum that has purple flowers, it has the natural purple pigmentation. And you can see that the phosphorus deficiency symptoms on the lower leaves here are a very extremely dark purple coloration. So it can range anywhere from kind of more of a red to a purple coloration. But it's important to know that you may be supplying phosphorus to the plant and still see symptoms of phosphorus deficiency occur. And one of the reasons for this is that you may have limited phosphorus uptake due to root rot, which is the case in both of these photos here. So you can see when you're applying phosphorus, even though there may be enough in the substrate, if the roots are unhealthy, they're not going to be able to take up enough phosphorus, and it's going to lead to symptoms such as these. In a similar situation, you may be applying enough phosphorus and the roots may still be healthy, but if it's too cold or wet, the roots aren't going to be able to function properly, and that'll lead to more symptoms such as this. So it doesn't necessarily depend on the root health or whether or not you're supplying phosphorus, but you still may run into symptoms. And additionally, drought stress can also lead to these types of symptoms. If there's not enough water, the roots won't be able to take up any phosphorus that is in the substrate, and it will lead to symptoms such as this on the plant on the right. So now let's talk a little bit about the different mimics that may look a lot like phosphorus deficiency. So here you may see a bronzing or blackening of the lower foliage due to low substrate pH. Obviously, the symptom looks a lot like phosphorus deficiency, but is actually due to a toxic accumulation of iron and manganese that will occur at low pH. And if you want to read more about that, we've done a number of e-GRO alerts, e-GRO 329 there at the bottom of the slide. If you want to check that out, we definitely have some resources available for you to read. Next, you may see this red coloration due to a generally low EC or electrical conductivity. So if the salts are low, you'll see these types of symptoms develop as well. And so this isn't specifically due to low phosphorus, but just to low fertilizer salts in general. And additionally, a lot of people don't think of this, but sulfur deficiency can also manifest as a red coloration. So this is typically more common in plants that have a natural red pigmentation. You can see the healthy plant on the left has naturally red coloration in the stems and in the leaf petioles. And so when you have sulfur deficiency, that red pigmentation can become much more pronounced. And so the way that you could tell the difference between the sulfur and phosphorus deficiency is that sulfur deficiency is going to be more of an all-over reddening, whereas phosphorus deficiency is going to be more severe on the lower leaves. So that's one way that you may be able to tell the difference between these two types of deficiencies. So next, we'll briefly look at symptoms of olive green leaf spotting and necrosis. So here I wanted to illustrate that these symptoms can also appear on poinsettias. We saw how the symptoms of reddening looked on poinsettias, and you can also get these symptoms as well. So one single crop may be able to show multiple different types of symptoms, and that's really important to know. So you can see there's no reddening here, but there's a very chlorotic region that is just dotted with a very high number of these olive green leaf spots, and you can see those denoted by the white arrows. Next, I want to talk about upper leaf symptoms of phosphorus deficiency, and this has been a major topic of my research. So what can happen when the plant is in flower, but there's not enough phosphorus available? So again, going back to this mum, but now it's in flower. So what's happening is when the plant has reached maturation and is reproductive, and then you cut off any supply of external phosphorus through the fertilizer, what appears to happen is that the phosphorus will move from the lower leaves, as it typically would, and it moves up the stem, going to the deficient tissues. But now you have two competing sinks, one being the flower and the other being the upper leaves. And so in this case, the flowers take precedence as the plant wants to put more of its energy into reproduction, as reproduction is more important than its own growth and maturation. So again, a really atypical symptom that you wouldn't normally think about. And it's been reported from some growers. It was initially observed on mums, and it occurs as a necrosis of the leaves just below the flowers and flower buds. It seems to occur under conditions of low but sufficient phosphorus early on, but no phosphorus during flowering. So here is e-GRO Alert 362 if you want to read more about this initial report of the symptoms occurring on mums. You can see in the picture on the left that there's general chlorosis with olive green leaf spots that we just talked about. And in the picture on the right, you can see just kind of the all over necrosis and chlorosis just below the flower buds. And obviously this can be a very catastrophic symptom that can cause major losses in your crop. So initially we did an experiment on sunflowers trying to induce these symptoms. We grew sunflowers using 8 different rates of phosphorus, ranging from 0 to 80 parts per million. And after 6 weeks, some of the plants were switched to 0 parts per million phosphorus just to cut it off, but they still were receiving the same amount of all of their other fertilizer nutrients. And so we got pretty good results here. We got these symptoms of a pale green coloration occurring just below the flower. The picture on the left, you can see that. And after just a couple of weeks, that pale green started to become a very pronounced red coloration with necrosis of the leaves just below the flower. And this is really interesting because the central leaves of the plant still remain green and healthy. So we were able to successfully induce these symptoms on sunflowers grown with an initial phosphorus rate of 10 part per million phosphorus. And so what we saw is that higher rates did not develop these symptoms, while lower rates developed typical lower leaf deficiency symptoms. So this experiment really helped us to refine our rates for our second round of experiments. So next we did an experiment on mums. You can see here's a yellow cultivar here. And if you look, we used concentrations of 10, 15, and 20 parts per million, which were then cut off after 4 weeks of growth. And we cut them off at 4 weeks of growth because that's when they started to develop flower buds. And so you can see the plant on the left that was grown with an initial concentration of 10 parts per million phosphorus has some necrosis in that central area of the plant. And even you may be able to see a little bit on the upper leaves. But if you look at the lower leaves, they still So here's 10 parts per million phosphorus. The picture on the left, you can see just below the leaves, there were these symptoms of marginal chlorosis and necrosis. And in the picture on the right, you can see that necrosis quickly became more of a curling, and the leaves definitely went very downhill very quickly. And again, you can see that it's mainly affecting the reproductive leaves of the mums, and that's the leaves just below the flowers, and they're the very unlobed leaves of mums. And just looking at the base of this plant, you can see that for the most part, it was green and healthy. And you can see I have just a little arrow pointing. There's a little bit of necrosis that's occurring a little higher up on the stem. So again, really unusual symptom that you wouldn't associate with phosphorus deficiency. And we did the same experiment with a different cultivar. This is Crystal Misty Purple. And you can see that it really reacted very differently than the yellow cultivar. And it's important to note that these mums were grown at the same time on the same bench. So they had the same conditions for growing. And you can see that the plant that was grown with an initial concentration of 10 parts per million phosphorus had very, very severe purpling of the lower leaves. And the plant that was grown with 15 parts per million initial phosphorus also had some purpling, but it was mainly on the upper leaves. You can see that the lower leaves are still green and healthy. So you can just see here that the reddening was very, very severe on those reproductive leaves just below the flowers. And if you look kind of in the background, you can see that it's mainly green lower down on the plant. So very severe purpling on the upper foliage that pretty much encompassed the entire leaf. And another interesting thing to note is that if you look closely at the stem of the flower, the stem is also turning purple. And that's a symptom that we did not see occurring on plants that were grown with a continuous supply of phosphorus. So we actually saw the purpling of the stem occur before the purpling of the leaves. So that might be a really good indicator that you're going to have some phosphorus deficiency symptoms occurring on the leaves very soon. But again, you didn't see the symptoms of reddening or purpling on the yellow mum cultivar. So it's important to know that maybe that cultivar does not have the ability to produce these red pigmentations, but this purple flowered cultivar definitely does. So in addition, we saw the necrotic margin curling occurring. The picture on the bottom left, you can see that occurring there. And then we also saw olive green leaf spotting. The picture on the top right, you can see that there was olive green leaf spots mixed in with the red coloration of that upper leaf. And I just wanted to show you a symptom progression I took of the reproductive foliage of this mum. Again, you can see the entirely unlobed leaves on the top row and the just very slightly lobed leaves on the bottom row. So these are all the leaves that you would see just under the flowers on this mum cultivar. And you can see that symptoms range from just chlorosis to chlorosis with reddening, chlorosis, reddening, and necrotic spots. In fact, if you look at the leaf on the bottom left-hand corner, second from the left, that one appears to have olive green leaf spots, necrotic leaf spots, chlorosis, and reddening. So you can expect to see pretty much any phosphorus deficiency symptom, even within one single leaf. So it's really important that you know all of these different symptoms and are able to recognize all of them, because they can all occur on a single plant. And then we also did this experiment using peppers. This is ornamental pepper Tango Red. And so this plant was grown with an initial concentration of 10 parts per million phosphorus that was cut off after 6 weeks. Again, at the point of 6 weeks, that's when they started to initiate flowering and were starting to set fruit. And so you can see that all the leaves appear green and healthy, except those couple that are directly below the peppers. And so those leaves kind of had a gray coloration, some chlorosis, and necrotic spotting. And if you look kind of at the leaf closest to the center, that one is actually abscising from the plant. Peppers have a tendency to drop their leaves very quickly when symptoms of phosphorus deficiency come in. And so that's a really important thing to note. And here's the same treatment of plants that were grown with an initial concentration of 10 parts per million. The plant on the right being given a continuous rate of phosphorus, and the plant on the left being cut off. And so this is just after 5 weeks without phosphorus, the plant completely collapsed. The majority of the leaves fell off, and you can see that there's still a number of necrotic leaves surrounding the edge of the pot. So definitely this proves that you really need to give plants phosphorus. You can't just completely take them off of phosphorus, or you may run into some really severe symptoms occurring. So again, we refer to this as a late season phosphorus deficiency, and the take-home message is that plants that are grown with about 10 to 20 parts per million phosphorus for half of the production cycle, and then 0 parts per million phosphorus for the other half, develop these symptoms on the upper leaves. Plants grown with less than 10 parts per million phosphorus develop typical symptoms on the lower leaves, and plants grown with more than 20 parts per million phosphorus just don't seem to develop these symptoms. Loading them with a very high concentration of phosphorus does seem to be able to get the plants through at least short-term greenhouse crops. It allows them to develop normally and not develop these types of symptoms. So now I want to move briefly into phosphorus toxicity, which is actually an induced iron deficiency, and it occurs as an upper leaf interveinal chlorosis. So here you can see the Scaevola plant that has very severe and classical symptoms of iron deficiency on the upper leaves, very pale yellow coloration with the green veins remaining. So this is a very common symptom for Scaevola and other Australian natives that are sensitive to high levels of phosphorus. Australian soils are typically very low in phosphorus, so any Australian native plants are adapted to these very low phosphorus soils. So when you supply them with too much phosphorus, they'll run into this issue. And so this occurs because phosphorus will tie up the iron and will lead to these interveinal chlorosis symptoms on the upper leaves. And this is because phosphorus and iron are antagonistic with each other. And you can avoid these types of symptoms by switching to a low phosphorus fertilizer such as 13-213 Cal Mag. So now let's talk about some of the conclusions. Low phosphorus fertilization can be a very effective strategy to control growth in many different greenhouse crops. You can take rates very low, but crops still need phosphorus for satisfactory growth. You can apply about 5 to 10 parts per million phosphorus, which is sufficient for most crops, as I've shown, and you can achieve these levels using low phosphorus fertilizers such as 13-213 Cal Mag at rates of 1 to 200 parts per million nitrogen, or 15-5-15 Cal Mag at rates of 100 parts per million nitrogen. So it's really important to note that there are a number of things that you can do. There's a number of commercial formulations that you can use to apply this general range of rates to your crop. So definitely keep that in mind. But you really need to use caution not to lower your phosphorus rates too low, or you might develop phosphorus deficiency symptoms. So again, 5 parts per million may not seem like much, but it's enough for the crop. But if you go much lower than that, there's a good chance that you may run into phosphorus deficiency symptoms. And again, these symptoms will occur as a purpling or reddening or necrosis in olive green leaf spots. Lower rates later in production can, if you were to use them to harden off a crop, for instance, that may result in late season symptoms below the fruits or the flowers. So if you supply a low but adequate rate of phosphorus for the first half of production and then limit the supply later on, you may run into these issues. Also, using excessively low rates of phosphorus may cause a delay of flowering in some plants or excessive stunting. But lowering your phosphorus fertilization strategy can help produce more compact plants. And of course, this is really beneficial for the floriculture industry. You can see a number of economical benefits, such as closer bench spacing. When you have shorter plants, you can potentially fit more shelves per shipping rack, which can help you to fit more into a truck. And plants are typically more attractive for consumers when they're more compact. Additionally, you can see environmental benefits. You can see reduced waste of unnecessary fertilizer and reduced runoff, which is of course better for the environment. Phosphorus has been a big issue with algae blooms and other water quality issues in recent years. So by limiting the amount of phosphorus you apply and limiting the amount of phosphorus that runs off, you can reduce any eutrophication that would occur in your local waterways and lakes. And so with that, I just thank you for listening, and I'd like to thank the Fred C. Glockner Foundation, the American Floral Endowment Altman Family Scholarship, and the Garden Club of America for their support of floriculture research here at NC State. So thank you very much.